Hi everyone, this is K. Karthik from Institute of Aeronautical Engineering and Electrical and Electronics Engineering from section 23951A0206. Now I am going to explain about crystal structures and magnetic properties of ferrum and copper multilayer films. Introduction to ferrum and copper multilayer films. Ferrum and copper multilayer films are a class of thin film material consist of alternating layers of iron, ferrum and copper Cu. These multi-layer structures exhibit intriguing magnetic and electronic properties that have attracted significant research interest, particularly in the field of spintronics and magnetic storage technologies. Ferrum and copper multilayer films are thin films structure composed of alternating layers of iron and copper. These multilayer exhibit unique physical properties that arise from the interaction between the different layers of nanoscale, making them a significant interest in various fields of material science and technology. Key features and properties: magnetic properties, structural properties, electronic properties. Applications: data storage, magnetic sensor, spintronics. The crystal structure of ferrum and copper multilayer films are a critical factor influencing their physical properties and performance in various applications. The properties of these films are heavily depend on the crystallographic orientation, lattice parameters and interface quality between the iron and copper layers. Here in overview of the crystal structure involved in ferrum and copper multilayer films. Crystal structure of ferrum and copper multilayer films. Ferrum or copper multilayer films exhibit a unique crystal structure due to the combination of the two different materials. The ferrum layer typically adopts a body-centric cubic BCC structure, while the copper layer have face-centered cubic FCC structure. The close lattice mismatch between the ferrous and copper layers leads to the formation of coherent interfaces, which can be tolerated by adjusting the layer thicknesses. The precise crystal structure of the ferrum and copper multilayer depends on factors such as deposition method, annealing condition, and layer thicknesses techniques like X-ray diffraction and transmission electronic microscopic are commonly used to characterize the crystal structure of these multilayer thin films. Magnetic properties of ferrum and copper multilayer films. Ferrum and copper multilayer films exhibit unique magnetic properties due to the interplay between the ferromagnetic iron and non-magnetic copper layers. The magnetic properties of these films are strongly influenced by bilayer and the interfacial interactions between the materials. At low ferrum layer thicknesses, the film often display super superparamagnetic behavior, where the magnetic moments of the ferrum layers are not strongly coupled. As the ferrum layer thickness increases, the magnetic moment becomes more strongly coupled, leading to ferromagnetic ordering and enhanced magnetic properties such as higher saturated magnetization and coercivity. Fabrication techniques of ferrum and copper multilayer films. Sputtering, versatile thin film deposition method, evaporation, vacuum-based film growth technique, molecular beam epitaxy, high controlled layer by layer growth. Ferrum copper multilayer films can be fabricated using a variety of thin film deposition techniques Spattering is a commonly used method where atoms are ejected from the target material and deposited on a substrate to form the multilayer structure. Evaporation is another approach, where the source material is thermally evaporated in vacuum and condenses on the substrate. For highly precise control over the layer thickness and interface quality, molecular beam epitaxy (MBE) is often employed, allowing the layer by layer growth with atomic scale precision. Influence of layer thickness on crystal structure. The crystal structure of ferrum or copper multilayer films is strongly influenced by the thickness of the individual layers. As the layer thickness decreases, the film tend to exhibit a transition from a polycrystalline to a more epitaxial structure. This is due to the increased role of interfacial effects and the suppressor of bulk-like behavior in the thinner layer. At larger layer thicknesses, the ferrum and copper multilayer maintains their respective bulk-like crystal structure, with ferrum typically exhibit a BCC structure and Cu a FCC structure. However, as the layer thickness is reduced to nanoscale, the crystal structure can become more complex, with the potential formation of metastable faces or highly strained interfaces. Influence of layer thickness on magnetic properties. 5 nm thin layer. At layer thicknesses below 5 nm, the magnetic moment of the ferrum layers are strongly coupled, leading to a collective magnetic behavior. 10 nm intermediate layer. As the layer thickness increases to 10 nm, the magnetic couple between ferrum layers weakens and layers begin to exhibit more independent magnetic behavior. 20 nm thick layers. Beyond 20 nm thick layer thickness, the ferrum layers are essentially decoupled, displaying their bulk-like magnetic properties with minimal interlayer interactions. The magnetic properties of ferrum and copper multilayer films are strongly depend on the thickness of the individual layers. At very thin layer thicknesses below 5 nm, the magnetic moment of the ferrum layer are tightly coupled, leading to a collective magnetic behavior across multilayer. As the layer thickness increases to around 10 nm, the magnetic coupling between ferrum layer weakens, and the layers start to exhibit more independent magnetic characteristics. Beyond 20 nm layer thickness, the ferrum layers are essentially decoupled, displayed the bulk-like magnetic properties with minimal interlayer interactions. Interfacial effects in ferrum and copper multilayer films. The interfaces between the iron and copper layers in multilayer films play a crucial role in determining the overall crystal structure and magnetic properties of the system. Atomic diffusion and interface mixing can occur at these interfaces, leading to the formation of intermetallic compounds or solid solutions. The degree of interfacial mixing is influenced by factors such as deposition condition, layer thicknesses, and annealing treatments. Additionally, interface defects and roughness can arise due to the lattice mismatch between ferrum and copper layers. These interfacial irregularities can affect the magnetic anisotropy and domain structure of these multilayers, as well as its giant magnetoresistance or GMR properties. which are crucial for many technological applications. Applications of ferrum and copper multilayer films. Data storage. Ferrum and copper multilayer films have been extensively used in development of high-density magnetic data storage devices such as hard disk drives (HDDs) and magnetic random access memory (MRAM). The unique magnetic properties of these films including their high magnetoresistance and thermal stability, making them ideal for applications in advanced data storage technologies. Spintronics. The spin-dependent transport properties of ferrum and copper multilayer films have led to their use in spintronics devices such as spin valves and magnetic sensors. These films can be engineered to exhibit a high degree of spin polarization, enabling efficient spin-based information process and sensing applications. Microwave devices. The high frequency magnetic and electrical properties of ferrum and copper multilayers have made them attractive for use in microwave devices, including filters, resonators, and phase shifters. These films can be soiled to exhibit desired frequency dependent characteristics, allowing for the development of advanced microwave components. Biomedical sensors, owing to their biocompatibility and magnetic properties, ferrum copper multilayer films have found applications in the development of biomedical sensors, such as those used for the detection of biomolecules or the monitoring of psychological processes. These sensors can be provided enhanced sensitivity and specificity compared to the traditional alternatives. Characterization techniques for ferrum and copper multilayer films. Magnetic characterization. Vibrating sample magnetometry (VSM) is a key technique for evaluating the magnetic properties of ferrum and copper multilayer films, such as saturation magnetization, coercivity, and magnet anisotropy, which are crucial for understanding their potential applications. Films. Structure analysis, phase identification, magnetic characterization. Structure analysis. Scanning electron microscopy (SEM) is a powerful tool for analyzing the cross-sectional structure of ferrum and copper multilayer films, revealing the distinct layers and enabling precise thickness measurements of each individual layer. Phase identification. X-ray diffraction (XRD) is a widely used technique to study the crystal structure and identify the phase presentation in ferrum and copper multilayer films, providing insight into the epitaxial growth and potential formation of intermetallic compounds. Conclusion and future prospects. In conclusion, the study of ferrum and copper multilayer films has provided valuable insights into the interplay between crystal structure and magnetic properties. The unique thin film architectures of these materials has enabled the exploration of novel magnetic phenomena such as interlayer exchange, coupling, and exchange bias effects. Looking to the future, there are numerous opportunities to further advance the understanding the applications of ferrum and copper multilayer films. Emerging fabrication techniques such as atomic layer deposition and molecular beam epitaxy offer the potential to precise control to layer thickness and interface structures, allowing for even greater tunability of the magnetic properties. Furthermore, The integration of these multilayer films into spintronic devices and magnetic sensors holds promise for revolutionization data storage, the information processing technologies. As researchers continue to push the boundaries of the material sciences and nanoscale engineering, the field of ferrum and multilayer films is poised to play a crucial role in shaping the technological landscape of the future. With ongoing advancement in both fundamental understanding and practical applications, the prospects of these intriguing magnetic thin films remain bright and full of exciting potential.